Assalamualaikum warahmatullahi wabarakatuh. Very good day. So for part number 7, we will discuss about the ideal gas equation of state. So before this, in previous part, we already learned about the pure substance that change in terms of phase from, for example, from compressed liquid to saturated mixture to superheated vapor. However, for this part, we will discuss about the pure substance in gas form or gas phase, where we will discuss the ideal gas equation of state. Okay, gas equation of state. So this is gas in terms of molecule arrangement, where we have for the gas molecule, the gas molecule will randomly move, and the molecule collide with each other and also collide with the wall of the container. Okay, in terms of property table for the gas, if you look in the thermodynamic textbooks, so you will have numbers of property tables involved with gas. Okay, so we have the ideal gas of air, ideal gas of nitrogen, ideal gas of oxygen, ideal gas of carbon dioxide, ideal gas of carbon monoxide, ideal gas of hydrogen, and the last one probably ideal gas of water vapor in terms of properties table. Okay, so this ideal gas of properties table will give you very accurate information about the gas properties. However, we will have bulky data, and the table actually vulnerable to typographical error. Okay, because we involved with many data, so sometimes we will tend to make error in terms of when we read or take what we call the data from the table. So we need to consider a more practical and simple approach with sufficiently general and accurate if you compare to the ideal gas properties table. So we can use the ideal gas equation. Okay, so the ideal gas equation is more practical and simple approach with sufficiently general and also accurate. This ideal gas equation will use to predict PVT, which is pressure, volume and temperature behavior of a gas. And the ideal gas relation, actually you probably already learned in your secondary school in physics subject, where we have PV equal to RT. PV for pressure, V small letters stand for specific volume, equal to R stand for gas constant, and T is temperature. Okay, so we have another similar equation, which is PV. Now V capital letter, so P is pressure, V is volume, equal to M small letter mass, gas mass, R gas constant, and T is the temperature. So any gas that obey the relationship is called the ideal gas. Okay, any gas that obey the relationship of PV-RT or PV-MRT is called ideal gas. Okay, so in terms of the parameter inside the equation, so P is equal to the absolute pressure, small letter V is specific volume, capital letter V is volume, and M, small letter m, is mass. R is stand for gas constant, so the general formula for R, for the gas constant R, equal to RU divided by capital letter M. So RU is the universal gas constant. The value is fixed, where the value is 8.314 kJ per kilomole Kelvin. And capital letter M stand for mass of 1 mole. And the last one, T, is represent the absolute temperature, and the unit must be in Kelvin. Okay, now for a fixed mass system, where the property of an ideal gas at two different states, as shown in the schematic diagrams. Let's say we have a piston cylinder device at state number 1. So inside the cylinder we have a gas with properties such as P1, pressure at state number pressure, volume, and also temperature at state number 1. So we just write down as P1, V1, and also T1. So after a period of time during the process, or at the final state, the state will be at state number 2, and the gas in terms of property will change into pressure, volume, and temperature. So we just you just state that the condition or the properties during state number 2 for the gas will be P2, V2 and also T2. So now we have two different states. So for this kind of process with two different states, we can implement the ideal gas relationship. So now for two different states, so we'll have this equation P1 multiplied by V1 divided by T1 equal to P2 multiplied by V2 divided by T2. So we can use this relationship. Actually, this relationship come from the basic ideal gas relationship PV/RT. Okay, so we can use for the system with a fixed mass with different properties for different states. Okay. Example 3.9. The gauge pressure of an automobile tire is measured to be 210 kPa before trip and 220 kPa after the trip at a location where the atmospheric pressure is 95 kPa. Assuming the volume of the tire remains constant and the air temperature before the trip is 25 degrees Celsius, determine air temperature in the tire after the trip. Okay, so data given, the substance will be air inside the tire. Before trip condition, P gauge 1 equal to 210 kPa, T1 is 25 degrees Celsius, volume is constant, where V1 equal to V2. After the trip, the pressure gauge state number 2 equal to 220 kPa, and the atmospheric pressure is 95 kPa. So for atmospheric pressure, actually the atmospheric pressure is the same for the condition before trip and also after the trip, and the volume is still constant, V1 equal to V2. So if we just draw the simple schematic diagram, so this is the condition before the trip and then the condition after the trip. Okay, so before the trip we have this specific condition where P gauge 1 equal to 210 kPa, T1 25 and P ATM equal to 95 kPa. Okay, so in order to obtain the absolute pressure for the condition before the trip, so P1 equal to P gauge 1 plus P ATM equal to 305 kPa. For the after trip condition, P gauge 2 equal to 220 kPa, T2 we doesn't know, so because the question asks you to determine T2, and P ATM is the same with the P ATM for the before trip condition, which is 95 kPa. So absolute pressure after the trip, P2 equal to P gauge 2 plus P ATM, which is equal to 315 kPa. Air is an ideal gas. Air temperature in the tire after trip T2 we can determine by using by implementing the ideal gas relationship for two different states or for two different condition. So now we have 1 represent the before trip condition, 2 represent the after trip condition. So P1 multiplied by V1 divided by T1 equal to P2 multiplied by V2 divided by T2. So we want to know T2, so rearrange the equation, so we'll get T2 equal to T1 multiplied by P2 multiplied by V2 divided by P1 multiplied by V1. So we just substitute all the value that we have. So now if you look, because the volume is constant, so V1 equal to V2, so we can cancel out the term for V2 and also V1. So the remaining term for T2 equal to T1 multiplied by P2 divided by P1. So we already have all the data for T1, P2 and also P1, but we need to remember that to use the ideal gas equation, T must be in Kelvin and P must be in absolute pressure. Okay, so we have 25 plus 273 in order to change the unit from Celsius, the temperature unit from Celsius to Kelvin, multiplied by 315 kPa divided by 305 kPa. So in terms of temperature, so we'll have T2 equal to 307.77 Kelvin. Or if you want to have the temperature in degrees Celsius unit, so you need to subtract with 273. So in Celsius, the temperature will be 34.8 degrees Celsius. Okay, now we want to look at whether the water vapor is we want to know that whether the water vapor is an ideal gas or not. Okay, so the statement actually depend on the water vapor condition. Okay, whether the water vapor is ideal gas or not actually is depend on the water vapor condition. Okay, so this diagram shows the TV diagram for the water. So as we learned before, so we have what I call the saturation line, as shown by the black color curve, and we have the constant pressure line that represented by red color line. Okay, so we have three different regions. So we have compressed liquid region, we have saturated mixture region, and also we have superheated vapor region. So the red color area, as shown in this TV diagram, represent the superheated vapor region for the water. Okay, and we have the what I call the border that represent by the what I call the blue color dash line. So this line actually is the border between the superheated vapor and also the ideal gas region for the water vapor. Okay, so this blue color region represent the region for the ideal gas properties for the water vapor. Okay, so the value on the constant pressure line within the superheated vapor region actually represent the error percentage value. Okay, so for the ideal gas region actually is the region where the error percentage value is less than 1%. Okay, the selection of the ideal gas region in this TV diagram based on the value of error percentage value. So we can see that within the ideal gas region for the water vapor, so we can see that the value is less than 1%. So here we can see 0.8, 0.1, 0.2, 0.0, and so on. Okay, so the area where the error percentage value less than 1%, we consider that the water vapor will act as an ideal gas. Okay, so if we look the what called constant pressure line of 10 kilopascal, so the water vapor pressure below than 10 kilopascal regardless any temperature value, so the water vapor act as an ideal gas. Okay, for example, for air conditioning application where the water vapor temperature within -10 to 50 degrees Celsius and the water vapor pressure is less than 10 kilopascal in terms of partial pressure of water vapor inside the air. Okay, so for the air conditioning application, the water vapor inside the air we consider as ideal gas due to the temperature range and also the pressure range. However, if we look for the pressure line between, let's say, between 10 megapascal and also 15 megapascal, let's say the temperature is between 400 degrees Celsius and also 600 degrees Celsius, and this temperature range and also pressure range is what I call one example of the temperature range and also the pressure range for the steam turbine application. So we have the water vapor temperature is around, let's say, 400 to 600 degrees Celsius, and the water vapor pressure range inside the turbine is around 10 to 15 megapascal, for example. Okay, so the yellow color region represent the region for the steam turbine application in terms of water vapor condition. So for this case, water vapor is not an ideal gas, so we cannot treat the water vapor for the steam turbine application as an ideal gas. So water vapor for the steam turbine application is not an ideal gas. So that's why whether the water vapor is an ideal gas or not, actually it's depend on the water vapor condition. So we have two conditions here. Okay, so that the answer for the question if somebody asks whether the water vapor is an ideal gas or not. Okay, now about the compressibility factor. So this factor actually want to show how a specific gas deviate from its ideal gas behavior. Okay, so we want to know how far or how close gas deviate from the ideal gas behavior. Okay, how far specific gas deviate from its ideal gas behavior. Okay, so gases deviate from ideal gas behavior significantly at state near saturation region and also critical point. So this is TV diagram. If you look, this is the critical point, and this is the saturation line that close to this critical point. We can see that the numbering on the constant pressure line represent the error percentage value. Okay, so the error actually compare with the the value of the ideal gas behavior. Okay, where the error calculation in terms of percentage equal to the specific volume from the table, data table, minus what we call the specific volume by using the ideal gas relation, divided by the specific volume from the table multiplied by 100. Okay, so if you look the area that very close to the critical point and also the saturation line, we can see that the error quite high. For example, we have the point for the what we call on the constant pressure of 20 megapascal and close to the saturation line, the error is 56.2%. Okay, so on the point on the saturated vapor state that close to what we call critical point is around 152.7% in terms of error and so on. So the green color region represent the area with higher value of error percentage. Okay, so this the area with higher value of error we consider as non-ideal gas. Okay, non-ideal gas. So we need to describe this what I call the deviation from the ideal gas behavior for specific gas by using specific factor that we call compressibility factor, that represented by Z symbol. And the formula will be Z equal to PV divided by RT, or V actual divided by V ideal, specific volume actual divided by specific volume ideal. Okay, so this value will show how a gas deviate from ideal gas behavior. So this second graph shows the relationship between Z, the compressibility factor, with the reduced pressure PR for different different type of gas. Okay, so different type of gas represented by different data symbol such as X, circle, triangle, and so on. So you can look the specific gas by referring to the legend state in this graph. Okay, TR, the reduced temperature, equal to the current temperature given divided by critical temperature. So for each individual gas will have different critical temperature, and PR stands for reduced pressure, which is equal to pressure given divided by critical pressure. Okay, same as the critical temperature, each gas will have its own critical pressure. The dotted red line represent the value of Z equal to 1.0. So any gas that on this line will consider as the ideal gas, or will have the ideal gas behavior. Okay, so the dotted green color line which is equal to 1.0, which is PR equal to 1.0. So this line represent the line where the pressure will be equal to critical pressure, and TR equal to 1.0 represent the condition where the temperature equal to critical temperature. So this is what I call the relationship between Z and also the PR value for different type of gases. Okay, so in order you want to implement this compressibility factor, what I call for the gases within the non-ideal gas region, so you need to consider the value of Z, okay, for different type of gases. Okay, that's all I think for in terms of the explanation for the compressibility factor.